All right, so moving on to Module 21, which is all about community succession. So, what happens to a community after disaster occurs, or how do communities start to begin with? So, looking at our succession, what we're going to look at is ecological succession. So, ecological succession is going to be predictable replacement of one group of species by another group over time. So, three parts there: predictable replacement of one group by another group over time. So, pretty much every community is going to experience ecological succession at one time or another, and it can take from decades all the way to centuries. So the first type of succession we're going to look at is primary succession. So primary succession is ecological succession that starts with bare rock. So initially that area is devoid of soil, meaning that there's no soil to begin with. So usually that's when you just have exposed rock to begin with. An example of how that can occur is when you have exposed rock after a glacier moves, or you can also look at lava that's hardened, and you have that magma that's hardened over time, and you can start communities off of that eventually as well. So the way this works is you have this rock that's been exposed, and then you have these early colonizers come in. So things like algae and then other low-lying plants and the lichens. So they're going to grow within those rocks, begin to break that rock apart, and eventually they're going to help start to form soil. So eventually that soil is going to be inhabited by other species, and then those plants are going to live there, make it more fertile, they'll die, make it even more fertile, and then so on and so forth until you can have these bigger plant species and you can develop these distinct communities. So secondary succession is like primary succession, but it doesn't start with bare rock. So really it's just going to start with soil. So this is usually what's going to happen when there's some sort of disaster or some change in an ecosystem where the ecosystem is not completely destroyed, but the plant life goes away. So you have some sort of ecosystem disturbance. The soil is left mostly unharmed. You have new plants come in and colonize, and those early plants pave the way for later plants. So this can happen on smaller scales too. It doesn't have to be like a wildfire comes in and wipes out an entire ecosystem. It can be as simple as a tree falling in a forest. So if a tree falls in the forest and then that land underneath it is exposed to sunlight where it hasn't been exposed before, you can start to have secondary succession there. So when you have this sunlight that's going to come through, that makes that area hospitable for species of plants that rely on that sunlight. So usually the only plants that are going to live there are shade resistant plants, but now you open up that community to new plant life. So most scientists, or some scientists, believe that secondary succession ends with what we call a climax stage or a climax forest. So your old growth forests would be categorized as climax stages or climax forests. So that's kind of like what this is all leading up to. It's this beautiful, lush ecosystem. But many disagree with that as well, because at any time it can come and be reset. There's no end-all be-all. At the same time, there's not really, climax forests, yes, but then you also have ecosystems that are never going to have this abundant plant life. So let's break this down and look at it step by step. So starting with primary succession, you have rock that's exposed. Your early arriving plants are going to come in and they're going to colonize. They'll start to break down that rock. And then soil is going to become hospitable for root systems. So this is where secondary succession is going to start, is with that soil that's hospitable for plants. So then plants like grass and wildflowers, ones that are going to easily disperse, they're going to start growing there because they're going to they're going to have been brought in by whatever means that those plants reproduce. So the lives and deaths of those plants are going to help mature and enrich the soil. And now, new species can come in, ones that need more nutrient-dense soil. So the ones that come in are often called pioneer species. So at this point in time, species can come in and they can just overtake the community really quickly. Those are our pioneer species. Species that colonize new spaces rapidly. So they can come in and eventually they might end up out-competing that grass and those wildflowers, especially things like trees that are going to cast shade down on the grass and wildflowers and stunt their growth. So lastly, communities are going to keep growing. and they're going to grow based off the biome that they're in. So you're going to have these beautiful tropical rainforests, or you might have a desert region. So all of those started at some point with our primary succession. So succession doesn't just happen in a terrestrial sense. You can also have aquatic succession. There are two types of that. The first is tidal succession. So this is when you have a period of high tide followed by a longer period of low tide. So when there's that low tide, you're going to have this area of rock, this area of land that was once covered with water. When it was covered with water, it might have been hospitable for a bunch of different plant and animal species, but now that it's exposed, it's not hospitable for them. So all of those plant and animal species are going to die off. Eventually, that tide might come back in, and then you're going to have those original plants come back in and colonize the area, and then eventually all those other plants and animals can come back as well. Then we also have succession in lakes. So if you remember a couple of modules ago, or more than a couple of modules ago, we talked about the 3 different types of lakes, and they had varying depths based off of sedimentation. So that was an introduction to succession in lakes. So over time, naturally, sediments will begin to accumulate on the bottom of lakes. Human actions are going to make this worse. So things like farming or overusing soil and stripping them of their nutrients and really drying it out makes them more susceptible to erosion. So erosion can make lake succession go a lot quicker. So you have these sediments that accumulate on the bottom of the lake over time, and eventually that lake's going to become more and more shallow until eventually it's all the way filled in and it becomes a terrestrial ecosystem. So looking at what types of species are going to inhabit different biomes and different ecosystems. So this relates directly back to that community succession. So what's able to grow there over time? So species richness, or the number of species that are going to exist in an ecosystem, are influenced by 4 major things: latitude, time, habitat size, and distance from other communities. So talking about latitude, this is one that kind of stumps scientists. So we know that near the equator it is more species rich than it is to the north and the south of the equator. So slowly and slowly, as we move away from the equator, there are fewer and fewer species. So that might seem like it makes sense initially, because you think to yourself, oh, that's where tropical rainforests are. We know that it's really biodiverse, but why? That's the question that we have to ask ourselves, is why is this so biodiverse here? And you might think to yourself, well, because it's so moist and it rains a lot, and so it's great for different plant species. But there are also plant species that do just fine in the warmth without rain as well. So those plants that live in the deserts. So we don't know exactly why, but as you move away from the equator to the north and the south, you have fewer and fewer plant species and even animal species. So the second thing that influences species richness is going to be time. So the older the ecosystem, the more the species. And that's going to be for several reasons. So the older the ecosystem, the more diverse that ecosystem can become, and the more ecosystems you can have within an ecosystem. So time is going to increase the amount of species that can live within an ecosystem. The last 2 are going to tie together within this theory of island biogeography. So this is a theory that demonstrates the dual importance of habitat size and distance from other communities in determining species richness. So this graph here shows on our x-axis we have island area, and on the y-axis we have number of bird species. So you can see as an island got bigger, you had more and more species of birds that lived there. And so these 2, from this graph, you can see that the numbers correlate, and we can also assume causation from this graph as well. And there are 3 reasons that these 2 are related to one another. So first of all, we believe that dispersing species are more likely to find large habitats than small habitats. So the size of the habitat matters, because if one individual is going to leave their initial ecosystem and they're searching for a new ecosystem, if it's a large ecosystem, it's just going to be easier to find. The second reason is going to be that larger habitats can support more species. So you're going to have fewer of those limiting resources. There's not going to be as much competition when you have a large habitat. So naturally, you can house more species. And then last, within a larger ecosystem, you can have a wider range of environmental conditions, kind of like what we talked about with time too. So then you look at that distance from other communities. So are they completely isolated from another community, or can individuals from one community get there more easily? Can they migrate from community to community? If they're not isolated from one another, you're going to have better flow back and forth, and so you can have more biodiversity in those ecosystems that are close to other ecosystems. So looking at the issues with this, habitat islands, so we talked about islands here, our island biogeography. They're not just physical islands that are sitting out in the ocean. You can also have these habitat islands on the earth as well, these terrestrial, or not on the earth, but on earth. So you can have these terrestrial biomes that become isolated over time, and that's not a good thing. We don't want isolated communities. So in class, we talked about metapopulations and corridors that connect ecosystems, and we talked about how important they are for limiting the inbreeding depression. So when we have isolated communities, we form these habitat islands where habitats are distant from one another, and therefore animals cannot move back and forth. So sometimes this is human caused. So here's a picture of Yellowstone National Park from above, and you can see the mountains in here. Around Yellowstone National Park though, the land has become pretty harsh for different animal species that live within Yellowstone. So remember we talked about the three choices that animals and plants have. They can either, they can adapt, they can move, or they can die when they're faced with problems. So clearly, if they become isolated within the park, they can't move, because if they try to move, they're not going to make it to the next ecosystem because they've become so isolated. So overall importance of this is that we want to be able to connect communities to one another, and when a community collapses, eventually it can kind of revitalize itself, but that process can take quite a long time. And that is all that we have for Module 21.